Hello everyone, this is your first team lab or open-ended design lab. This should be similar to what we used to have when we were running physical laboratories. So I'm hoping this should excite you more. So we're doing the verification of the Thevenin equivalent circuits. You should go through this theory, but briefly, when we have a circuit with the varying loads, if you want to calculate the voltage and a current in a complex circuit, each time you have to do complex calculations involving mesh currents or node analysis. But if you could rather have this circuit represented, so the circuit excludes the load, of course. If you could represent it with a very simple circuit, which is called the Thevenin equivalent, then your task would be so much easier. Just the voltage division formula can give you the voltage across the load, and the currents can be easily calculated. So this is going to be our task here. In order to convert or get the Thevenin equivalent, first of all, you need to remove the load, and the first thing you would do is to calculate the open circuit voltage. So when you remove this one, basically you're looking to calculate the open circuit voltage called VThevenin. And the next thing you would do is to calculate the RThevenin seen by these terminals. But before doing that, you should remove the DC source and put a wire after you remove the source. And then using a multimeter, then you can measure how much resistance it has. Then you have this equivalent circuitry that you could use to calculate load currents and voltages at different RL. So it makes our life very easy. In this lab, you have a design problem. So we're giving you this circuitry, a similar circuitry like the one above. Input voltage is specified, and we got the resistors given as R. So they're identical resistors, and you have to figure it out, figure their values. First of all, you should prove that VThevenin of this circuitry, when RL is removed, of course, is 2.5 volts. So you can easily, hopefully, show it to me that this is the case. And this is the actual information you will use to figure things out. So it's giving you the voltage at the load when the load is at 1 kilo ohms. So when RL is 1K, VL is 0.7 volts. So you can refer to the voltage division circuit or the Thevenin equivalent circuit to figure the value of our Thevenin, because you know how much the value here and how much is the voltage, and you know what the VTH is, so you can easily figure the value of RTH. Now, referring to figure 5, you should be able to formulate our Thevenin as well. Once you turn this one off, this one is removed, of course, and looking through these two terminals, you should be able to figure the value of RTH in terms of R by using a simple formulation. Then, since you got RTH from the previous step, you can easily now figure the value of R. So we have the values. Then you can do a multisim simulation in Prelab 3. So we simply construct circuits in figure 5 and figure 6 and try to see if the values of VL match to each other. You will then verify the maximum power theorem in Multisim. So in step 6, what we're doing is we're setting RL value to 50% of, starting from 50% of the RL optimum all the way to 1.5 RL optimum in steps of 0.1 RL optimum. So for each value of the RL, you're going to be recording the output voltage value and create a table with the power consumed on each one, and finally state which one gives the maximum power on the load. You should get the power maximum at the RL optimum value. And finally, we're constructing the circuit in analog discovery and the breadboard using the breadboard. The value you find for R should be straightforward, so you don't need to do any resistor combinations. So once you construct the figure 5, you record the load voltage, and then you repeat it with the Thevenin equivalent, and I'm hoping that RTH can easily be constructed using few resistors that is in your component box. And you again compare to the measured values, compare the two values, and then compare to the measured values in Multisim. And finally, you verify the maximum power theorem. Now your load is varying. That's why we're gonna be using a variable resistor called trimmer. You can only use either the first two or the last two terminals. What you should do is to set the value of RL using a screwdriver, and a multimeter measures how much resistance it got. So you might start with 0.5 RL optimum and go up. And we got a bunch of questions. Now, as far as the dividing this work, I have some guide here which you can follow. So I'm trying here is to let everyone do a portion of the analog discovery. So you have some exposure. So I'm open to other proposals, but make sure it is divided equally. Now, if it turns out that team member 1 is not doing analog discovery and mostly simulations, make sure this team member next time around does the analog discovery, so rotating the roles. Unless you specify a week before the deadline your proposal, we will assume this will be the division of duties. And on the lab report, you need to state which member is doing which part. And remember, there will be collaborate presentation where you will need to present. So it's a good idea to have those in the lab report. And if any difficulties, please let us know. But this should be a straightforward lab. Thank you.